नमस्कार। इस छोटे से वीडियो लेक्चर में मैं एक महत्वपूर्ण रिजल्ट डिस्कस करना चाहूँगा, जिसको हम गैल्वा ग्रुप के कंप्यूटेशन में फ्रिक्वेंटली यूज करेंगे। तो हम प्रोपोजिशन 2 पे आते हैं। फर्स्ट वी wish to prove that this proposition here L1 and L2 be any two field extensions of a given field. Suppose that sigma is a homomorphism, K homomorphism from L1 into L2. Remember the definition of K homomorphism. Homomorphism which fixes every element of K. Next, suppose that alpha be element of L1 which is algebraic over K and Px is its minimal polynomial. Then our aim is to prove that the image of alpha under homomorphism sigma, that is sigma alpha, will also be algebraic over K with minimal polynomial Px. Means alpha and sigma alpha both have the same minimal polynomial. Now, if we take L1 is equal to L2, then this result suggests that if sigma is an automorphism from or homomorphism from L into L, then sigma permutes the roots of minimal polynomial Px. Minimal polynomial Px means if alpha is a root of minimal polynomial, then its image sigma alpha will also be a root of minimal polynomial. So, to prove this, suppose that sigma is a K homomorphism and alpha is algebraic over K. Also suppose that Px is minimal polynomial and is given by a0 plus a1x plus a2x square plus an minus 1 x power n minus 1 plus x power n. Remember that minimal polynomial is a monic polynomial. So leading coefficient will be 1. So here last term will be x power n and the coefficients a0, a1, a2, an minus 1 belongs to k. Now, since Px is a minimal polynomial of alpha, therefore alpha satisfies this polynomial, means P alpha will be 0. This follows from the definition of minimal polynomial. Now, we use the property of homomorphism. If sigma is a homomorphism, then it carries additive identity to additive identity. So, sigma of 0 will be 0. Now, sigma of 0 is equal to 0. Now, 0 is equal to a0 plus a1 alpha plus a2 plus dot plus alpha power n, because alpha satisfies the polynomial Px. So we can put this expression in place of 0, and sigma is K homomorphism, so it fixes coefficients of K, and so here sigma is a homomorphism, field homomorphism, so it preserves addition and multiplication. So we we distributed sigma on every term of this expression. So finally we have a sigma a0 plus sigma a1 plus into sigma alpha plus dot sigma an minus 1 sigma alpha whole power n minus 1 plus sigma alpha power n. Note that sigma is a homomorphism, so sigma of x power n can be written as sigma x whole power n. So this expression becomes this. But sigma is a K homomorphism, so sigma fixes elements of K. It means sigma a0 is equal to a0, sigma a1 is equal to a1, and so on. So we substitute this, and finally we have right side of this term will be a0 plus a1 sigma alpha plus an minus 1 sigma alpha power n minus 1 plus sigma alpha whole power n. This shows that sigma alpha satisfies the polynomial Px because this expression is 0. Left hand side of this expression is 0. So we have sigma alpha satisfies the polynomial Px. It means sigma alpha is also algebraic. Remember the definition of algebraic element. But note that every minimal polynomial is irreducible. And also remember that minimal polynomial of an algebraic element divides the polynomial fx which is satisfied by that algebraic element. So here px is a polynomial satisfied by sigma alpha. Therefore, minimal polynomial of sigma alpha divides px. But by property of minimal polynomial is irreducible. It means px is irreducible. So it has only one factor, a non-trivial factor, which will be px. That is px minimal polynomial of sigma alpha is also px. So what we have here, we have if alpha is a root of px, then sigma alpha is also a root of px. It means sigma permutes the root of px. Okay. So this proposition suggests us to define the following notion: key conjugate. Let L be a field extension of a given field K. Then any two elements alpha and beta are called K conjugates if there is a K automorphism which carries alpha to beta. So by this definition, here we have some examples. Observe that phi is a automorphism of C, conjugation map is a automorphism of C, or automorphism of C, which carries I to minus I. It means I is R conjugate to minus I. Next, identity map I carries I to I, therefore I is also R conjugate to I. It means here we have discussed that I and minus I is R conjugate. Similarly, one can prove that omega is Q conjugate to Q itself in the field Q omega. Omega is algebraic with minimal polynomial 1 plus x square, and note that omega is conjugate to omega itself. Here omega instead of q, there is a slips of mistake. This will be omega. Omega is conjugate to omega itself. Here are some questions. Try to prove this. Now, using above result, we wish to prove that the following corollary. It gives certain ideas which we will discuss in incoming video lectures. Suppose that L is a field extension of given field K. Let alpha be algebraic over K. Then our aim is to prove that number of K conjugates to alpha is at most degree px. where px is a minimal polynomial of alpha. मीन्स हम क्या कहना चाह रहे हैं कि अल्फा के कुल कितने के कॉन्जुगेट्स मिलेंगे, उतने ही मिल सकते हैं अधिक से अधिक जितना कि अल्फा का जो मिनिमल पॉलीनोमियल है उसकी डिग्री। तो अल्फा के मिनिमल पॉलीनोमियल की डिग्री से ज्यादा अल्फा के कॉन्जुगेट्स नहीं मिल सकते, यही हम कहना चाहते हैं। सो टू प्रूव दिस, suppose that alpha be algebraic over K and Px be a minimal polynomial of alpha over K. Since any K automorphism promotes the roots of Px, we have discussed in previous proposition. Therefore, permutes the roots of Px, it means it carries roots to roots. So, the number of if beta is k conjugate to alpha, then beta will also be root of minimal polynomial px of alpha. It means number of conjugates of alpha is at most degree px. Here are some examples. I hope that you will discuss it. You will solve it and observe that in this example I has two conjugates, one is I and other is minus I, and also the degree of minimal polynomial px is x square plus 1 whose degree is 2. It means this is an example of a field extensions C of R where the number of conjugates of I is exactly same as the degree of its minimal polynomial. Try to find some field extensions where number of conjugates of algebraic element alpha is equal to the degree, exactly equal to the degree of px, and also find where the number of conjugates of algebraic elements is less than the degree of its minimal polynomial. Okay, this example is a guiding example. Try to observe that this has only one root. This has only one root. This has only one root. Although this is a minimal polynomial of degree p. So this is an example of fixed extension in which an algebraic element alpha has only one conjugate, while the degree of its minimal polynomial is p. So this is an example where the number of conjugates of alpha is less than the degree of its minimal polynomial. Thank you. I will discuss further results in next video.